Thank you for the introduction, and thank you very much for having me. I would just like to clarify that the work I will be talking about was done during my time at UTS, and it has nothing to do with Google. So yeah, not an official Google announcement by any means. Very important. So these were my collaborators. Jack Cerrone, who is a student at the University of Toronto, and he was working with us while he was doing an internship in Xanadu. Torrens was our resident chemist, helping us with all the chemistry stuff. Carlos is a researcher at Pacific Northwestern National Labs. Many of you maybe know Juan Miguel from Xanadu, and Nathan Weeb, who works at Toronto. And as it usually goes, Jack is the one who did all the hard work, and he is actually an undergraduate student. So yeah, a very, very impressive guy. Okay, so what I will be talking about, I will spend a lot of time on the motivation, why we thought that this problem is interesting, how we thought about it, and what are some other related problems that you can maybe consider in your work. Then I will tell you about our algorithms. And it is fundamentally a heuristic algorithm, but we were able to give some rigorous guarantees on some parts of the scaling. And lastly, I will give you some lower bounds. So as someone who quite likes complexity theory, it's always good to spoil some of the fun and tell you what your work cannot achieve. So quantum machine learning is a pretty hot topic right now. We know that there is a lot we can do with a quantum computer. There is a lot we can do with machine learning techniques. So it seems just natural to put them together and see what we can do if we learn some machine learning algorithms on a quantum computer. Can it help us with anything? And in the last few years, we had quite a few really, really exciting results. I will mention just briefly a few of them. But if you talk to people with money, investors or CEOs of companies, like the question is, can quantum machine learning actually do anything? Like, it is nice that you have these theorems and you have these toy problems where you show some exponential separations, but can it really help us with problems that some people actually care about? And this is actually a really, really hard problem, because classical machine learning is really, really good. Might not be good about giving you factual information, but in many ways it is very precise. We now have the ability to train models with billions of neurons that can be trained very, very efficiently. They don't consume that much energy when you run them, and they are just really, really wonderful. There are some new improvements pretty much every few weeks. And compared to that, quantum computers are kind of lying. Like, it'll probably take a while until we have million logical qubits, and compare that with billions neurons. That is much cheaper to have and play with than even million logical qubits. And on the top of that, we know that quantum machine learning is plagued by a lot of problems. Reading in large data sets is really difficult. We know that you cannot possibly do that efficiently in many cases. One of the problems I spent some time looking at is trainability. We don't have backpropagation in quantum machine learning. We don't know if it could possibly even exist. So quantum models are very, very difficult to train. Yes. Yeah. So you don't have the same scaling in the number of parameters as with with the classical backpropagation. That is one problem. And the second problem is the gradients tend to be just exponentially small most of the time. So they're parameter shift rule is a really good result that people have been working with, but still the trainability is quite a big problem pretty much everywhere you go. So the type of quantum machine learning that I like to think about that I think has some nice properties is when you allow the quantum computer to cheat. You allow it to have access to something that is not really possible for classical computers, and that is quantum states. So one way how you can formulate quantum machine learning tasks is when you ask your quantum computer to learn directly from classic quantum data, quantum states. For a classical computer, you still have to do some tomography, and that is an inherently difficult task. So by circumventing the tomography, you are giving quantum computers some type of an advantage. Or alternatively, you can ask your quantum computer to create a model that would be able to generate quantum states. And that's, again, something that doesn't really make sense as a problem for classical computers. Or, you can be extra and try to do both. You both train on quantum data and you ask it to generate quantum data. So these types of problems are sometimes referred to as quantum machine learning. There is one big problem with quantum, training on quantum data is that you can't really download it from the internet. We don't have, large quantum data sets that you could just, load into your machine and work with. So the question is, how do we get the quantum data that, would actually make some practical sense for us? So you can tell that I'm a theorist by this picture. So one idea that people have is that you have your trusty quantum computer, let's say that is fault tolerant, and you can run quantum computation on it. And then you can have some other device. You can think about it as an untrusted quantum computer or a quantum sensor, or maybe a quantum computer that you are trying to calibrate, and then you are able to connect those two computers, like with the special quantum connecting cable with the right port. And what this quantum cable does is that it allows you to take the quantum states from one computer, or like from this computer, as I'm calling it here, and then analyze them on your actual quantum computers where you can do computation on it. And this is actually a really, really good idea, at least in theory. So if you have the ability to process quantum data coherently and store multiple copies of them, you can achieve exponential advantage in the number of copies of quantum states. Exponential advantage is a really big deal in our world. So just to give you a very, very simple example of where it does, imagine that you have some unknown quantum states and you would like to estimate the purity of these quantum states. So if from your untrusted device you get the quantum states one by one, then you have to do quite a bit of tomography, and it turns out that this task is exponentially expensive in the number of qubits. But if you have the ability to store 2 copies of the quantum state at the same time, you can use swap test. And swap test is something that is very, very simple algorithm, and it will become efficient. So if you have the ability to have a quantum computer that can store your quantum data coherently, this is a massive advantage. And whether or not you call this quantum machine learning is another question, but it is some learning that quantum computer can very much help you with. Another way how we can think about quantum data is that it comes from some previous computation. So let's say that you are doing Hamiltonian simulation, or you are solving some differential equations, or you can try to solve a linear system. So let's say that you run Pedro's algorithm for linear systems, and the output of this algorithm is this beautiful quantum states that is an exponentially long vector. And depending, so you can't really read it out. You can run tomography and run the experiment exponentially many times, but maybe you only want to figure out some properties of the state. Maybe you want to do some binary classification or something like that. So in some cases, it makes sense to run a quantum machine learning algorithm on the output of a previous quantum subroutine. And people around Seth Lloyd and collaborators actually propose doing something like this for differential equations. So what we are doing is very much falls into the second category, and we will be learning something about parametric Hamiltonians. So if you work in quantum algorithms for quantum chemistry, you often assume that the Hamiltonian is the input to your model. So your friendly neighborhood quantum chemist writes you all the coefficients of the Hamiltonian, and then your job is to find the ground state. But if you ask a quantum chemist from a different neighborhood, maybe they don't have the Hamiltonian, because they might know what the molecule is. They very much know what the molecule is. They know it's the chemical formula, but they often don't know exactly how the molecule looks like. So for the example of the water here, we know that we have like oxygen and 2 hydrogens, but we might not know exactly what is the bond length, and we also might not know what is the angle between the 2 hydrogens. So we don't really have one fixed Hamiltonian that we care about, but instead we will have a family of Hamiltonians for different values of these parameters, theta and r. And for each r and each theta, we will get a different Hamiltonian with a slightly and maybe significantly different ground state and a different ground state energy. It turns out this is a problem that many people really care about. So people quite often care about the geometric optimization, or like how you should twist and turn the molecule to make it stable. The most famous example of this would be protein folding, really hard problem. People care about what would be the stable or metastable configurations for different molecules. What is the dissociation energy? So, how much energy do you need to add to the molecule to pull the 8 atoms arbitrarily far? So people can care about how the energy gradients, how the energy changes with the different versions of different values of the parameters, etc. The task that we set ourselves to solve is slightly different. Instead of working just with the ground state energies, we will work with the ground state themselves. So we will assume that someone somewhere gave us a few copies of ground states for certain configurations, and then we will try to come up with a model that would be able to output pretty much arbitrary ground state for pretty much arbitrary configuration of the parameters. Of course, some approximation of it. So the way how we thought about is that we can have some quantum algorithm. Typically, this would be quantum phase estimation that we will. So the way that you would compute the energy for some configuration. Let's say this doesn't work really well. Is there a laser on this? Okay. Okay. So let's say that for this point A, you can run quantum phase estimation, and if you had good initial points after some repetitions, you can compute hopefully the ground state energy of it. But if you wanted to understand how the landscape looked like, you would have to do this many times. So if you have a molecule with lots of degrees of freedoms, then this will of course scale exponentially. And also we know that the problem of quantum ground state energy estimation is QML hard. So even if we can solve it for certain configurations, some configurations can be just absolute, can be really hard. We might not be able to to figure out the energies for everywhere in the space. So instead of really manually trying all the possible configurations, we will try to come up with a model that will only take ground states from a few configurations and then try to generalize out of them. Okay. So how do we get our training data? We will be running phase estimation or some more advanced version of estimation, phase estimation, where we start with some state that has a decent overlap with our ground state. We will set our U to be time evolution with our Hamiltonian for some fixed configuration, and then we will measure the energy in this register. But remember that when we run phase estimation, we will also prepare the ground state in this last register. And if you just think about all the uses of quantum phase estimation, the ground state normally isn't really used because, quantum states by themselves are not that useful. People only tend to care about the energy. And this is, actually a pretty good thing for us, because if we are already running phase estimation to learn some of the energies, we can maybe squeeze a little bit more from our experiments and also use these quantum states for training of our model. And similarly, if you are one of the people who realize variational quantum algebra solvers, you can also get quantum circuits out of them as well. So when we set up to do this project, we wanted to come up with some quantum neural network that will take parameters of the Hamiltonian. It will be some, it will be some vector R. I will be skipping the vector arrow for a while. And then we want to output approximate ground state for different configurations of these Hamiltonians. But it turns out that we don't really have to work with a big quantum neural networks. In this case specifically, we were able to split the model into quantum circuits and a classical neural network without sacrificing the performance. So quite often this is not possible when you have a lot of entanglement in your model, but in this particular scenario, we just ended up having a tensor product structure. So this made our training quite a bit easier, and it's also maybe easier to think about it. The advantage of it is that the quantum model itself is quite small, because we are able to offload quite a bit of the computation on a classical processor. And if you compare the quantum circuits that we will be running, they are still quite negligible. The cost of running them would be quite negligible with quantum phase estimation. So this is still not a near-term algorithm, because you need to get the quantum data from somewhere, and this is likely a difficult task. But it is maybe not as difficult as we initially expected to be. But because getting the training data is so difficult, we are really focusing on minimizing the sample complexity, trying to get away with as few samples as possible. Okay, so let me tell you about the algorithm, starting with training data. So we have some Hamiltonian. Let's say that it has 2 free parameters in this case, and we will take some n different configurations, so now n different values of these parameters, and for each of them we will have m copies of quantum states. And now, of course, we will assume that both capital N and small m should be polynomial for our algorithm to be efficient. So we don't know how this landscape looks like. We only have quantum states from the black dots where you see them. This is the sketch of our algorithm. So we have these parameters of the Hamiltonian R that will go as an input into the classical neural network. the output of the classical neural network will define our quantum circuits. So we will be running different quantum circuits for different R. Same structure, just now slightly different values and types of these gates. And as an output, we would like to have some quantum states coming from the circuit that would approximate the energy of the ground state well for all these different different bond lengths with different values of the parameters, if this is possible. So the only 3 parameters, the only thing that our model needs to learn, it will be the weights on the neural network. Once we have the neural network, it will tell us exactly how our quantum circuit will look like. And every time we run the quantum circuits, we will get some trial states that eventually should be close to the true ground states, but during the training, we hope that they will be getting better and better as we are training our algorithm until the output, this state size will be very close to the actual ground state. So the training will be performed doing some version of a gradient descent. So in the numerical experiments, we use Adam optimizer, but just think about a gradient descent. The thing that remember, we are trying to get our trial states, this one, as close to our data states from our training set as possible. And the loss function we decided to work with was average infidelity. So we tried to work with some really, really fancy loss functions, but turns out that wasn't really possible or advantageous at all. So we ended up with a pretty simple thing. And when we have n different quantum states in our data set, so we will just simply average over all of them. Okay. So what would be a reason for not using infidelity? Well, in quantum machine learning, we have this phenomenon called barren plateau. Many of you probably heard me talking about barren plateaus using this exact same slide. And barren plateau means that when you start training your quantum neural network, all of your gradients are exponentially close to 0. So you are not really able to train it at all because you can't really see the model to improve. This happens with infidelity because if you start with, you have some known state, but you start with some random state, and the overlap between random state and your fixed state will be typically exponentially small. And even if you vary this trial state a bit, then statistically, the overlap will still stay exponentially very, very small. So you are not really able to move anywhere because wherever you are, all the points around you seem equally bad. So this tends to happen with most random initialization. So why are we still training with respect to infidelity? Why do we think this model is actually trainable? Well, that's because we don't start with a random state. We choose our initial trial states to have some prior information about the system. If you talk to your, if you talk to your Taurine or your other neighborhood friendly chemist, then they will tell you how you should initialize your quantum circuits such that the state that you will have will already share some similarities with the ground state. And the state we used here was the Hartree-Fock state. So our initial guess for the quantum model was already okay-ish. And then during the training, we started improving it. So you can see the quantum model as adding corrections to a classical solution. But we will see later on that these corrections will be actually quite significant. So this is an important point. If we didn't have a good guess, then we wouldn't be able to trade. Jakob?
Like, it doesn't seem like super important how good the guess is. It's just important that the gradient is steep.
Yeah. So in principle, yes, but for random states, you are pretty much guaranteed to have zero-ish gradient. So yeah, but if you have some objective function that will give you bigger gradients, then that's great. But typically, if the overlap is small, the overlap between the states that are nearby will be also small. So the difference between them won't really be significant to help you learn. Yeah. Okay, so if the overlap is small initially, then you can't really do it. So you need to find a state that will already have that will have an overlap with the final state that is not exponentially small, and this will be some mean field solution or a Hartree-Fock solution. So you start with a classical solution that that from experience or by talking to chemists, that they think this is a pretty good answer. It is, yeah, it has some overlap. Does that make sense? Yeah.
Yeah. Doesn't suffer from this problem of like being too close to the correct state.
Yeah, so like if your Hartree-Fock state is like already really good, then you don't really have to learn, and you don't really need a quantum computer. But in some region, Hartree-Fock can give you already a very good solution. But for problems where you would want to use a quantum computer for ground state computation, Hartree-Fock is usually not good enough. Once we go into really, really big, complicated molecule, Hartree-Fock might not be enough. There is a paper about it called something with orthogonal catastrophe with Bill Huggins. But for a while, Hartree-Fock seems to give us good enough overlap to do a few decades of progress, perhaps. Okay. So we have some initialization for our quantum circuit, and our quantum model will pretty much just any parameterized circuit. And the way how we choose all of these parameters is to be some small time evolution or parameterized rotations. So this little Hamiltonian HH will be fixed, but we won't really know what the angles are. If you make these circuits long enough, this will be very, very expressive answers. In principle, we can fix some of the angles theta, and we will only learn some of them. We can add some extra structure in it, but in principle, we have some quantum circuit where we stay with state 0, and if we apply this parameterized circuit, we will get our trial state. And it is important that this is how our parameterization looks like. It will make our computation easier. Dom? Yeah, so one thing you can do is that you fix, one way what you can do is you fix this initial gaze to prepare the Hartree-Fock, and then you start tinkering with all of your gates. Another way would be also to add a little circuit here that would prepare, so instead of these gates defining like θ4 to θ7, you can make that some fixed circuit, and you will be only training those later layers. This, makes some of those choices will be much better for you, but for our derivation, it is all pretty much the same. And then we will be training the classical neural network to minimize the infidelity between the trail state and our training data. So we have our expression for our infidelity. We compute, and we can analytically compute our gradients. for a, some general state, this is how it will look like. But if we use the ansatz in the form of the evolution to all the little Hamiltonian, we will get something like this. So what we now need to use our quantum computers for is to compute these two expectation values, or like semi-expectation values. We already saw most of these terms, so this will tell us something about the gradients in the classical neural networks. These terms HA are actually unitary operators. So, there is some non-zero imaginary part, and these two terms are actually quite similar. So this will be a reflection around the final state created from the quantum neural network, and we are looking at the expectation of that thing inside of our training data. The way how we can sample from these expectation values is using some variant of Hadamard test. So typically in Hadamard test, we use it to compute the real part of a unitary operator, but with some small changes, we can instead get only the imaginary part. But remember, with Hadamard test, we can only sample from these terms. We are not computing them exactly, and also there are quite a few of them in our gradient expression. So instead of estimating the gradients by computing every single term and adding them together, we can use importance sampling and only sample from all of these different terms for different training points and different HA operators. And thanks to some nice concentration of measure phenomena that will help us this time, the training is actually not terrible. So we say that we can only tolerate error epsilon in each of our gradient component, and we want to have confidence at least 1 minus delta that we obtained sufficient precision. Okay, so this is if you want to use sampling, but since we assume that we have a fault tolerant quantum computer, you could actually do better using some more sophisticated tools. So one technique that you could use is amplitude estimation. So instead of sampling from the amplitudes, you can use some techniques similar to Grover to estimate the amplitude directly, and this will give us quadratic speedup. And also, instead of sampling from all the different terms, we can implement them all coherently using a tool called LCUF, linear combination of unit terms. So this will give us a better scaling with error. We can get some better query complexity, but this also requires quite a few more qubits. And there is this big state preparation step because we need to prepare a linear combination over all possible unitary operations then can come up in our expression. But yeah, maybe it's worth it, maybe it's not. In the paper that I listed in the beginning, I gave 2 different approaches. Okay, so we ran some experiments, and this worked actually quite good. But if you play with quantum chemistry for hydrogen, pretty much anything works. We were looking at our model, and you can even see the model in here because it overlaps really perfectly with the ground state. But what we started learning with these experiments is that it really matters how we choose our training data. So in this case, we trained with 3 different bond lengths for this one, and here. And we could also see that our trial state has a very good overlap with the ground state, but the overlap with the Hartree fog is actually, not so large. And for some of the bond lengths, it was we deviated quite a bit. So, you can think that, yeah, maybe your initial answer was really, really good. You didn't even have to train. Actually, we changed our state from the initial one by quite a bit, and that helped us to get a better overlap with the ground state. So we went to slightly bigger molecules, and then we started noticing that how many different bond lengths we sampled really matters. So if you use only 4 different training data points, then our model wasn't really fitting well the ground state for increasing bond length. So this shouldn't really be surprising, but by adding more different configurations, we significantly improved the model. And lastly, or out of the examples that I will show here, we also looked at Hamiltonian that had 3 different parameters. So we worked with hydrogen ion, and here we had not only the bond length but also the angle between our molecules. And you can see that we again got a pretty good agreement between the energies outputted by our model and the true ground state. So this is great. We have we propose an algorithm. It agrees really well with what the ground state would be. Works for 3 examples. We are done. We can submit it to Nature and revolutionize everything, including routine folding. Well, this technique actually doesn't work that well if you go to bigger and more complicated examples. And let me explain to you why. So one problem that we touched on is how many training points do we really need? Can we get away with sampling only from quite a few configurations and learning this beautifully complicated model? Well, that's not really how this works. So for this lower bound, we used a version of Kramer-Rao bound. So we assume that the actual ground state for all the different configuration is parameterized by some true parameters gamma theta that describe it. And then we can think about our quantum machine learning model as trying to estimate the parameters of the underlying problem. From Kramer-Rao bound, we can estimate the variance of an unbiased estimator of the true model parameters depending on the data that we sampled from the model. And thankfully, Kiana already talked about quantum Kramer-Rao bound earlier. So I'm not going to go into a lot of details, and the final result from this wasn't actually all that neat. But we know that the number of training states will be inversely proportional. Different training states. No, the number of training states will be inversely proportional to quantum Fisher estimation, and we were able to quantify it. And 2 very special examples, 2 very special cases, is that the number of states we need will scale as 1/epsilon, which is also what we get from Heisenberg bound. And also, if we are trying to learn a model that exhibits barren plateaus, we can't really learn it because the number of samples would diverge. So if you want the technical version for it, go to the paper. I'm not going to talk much more about it. One thing just to mention is that the conditions for quantum Kramer-Rao bounds don't exactly model are not exactly satisfied in quantum generative machine learning. So the objective function that we are working with is not technically strongly convex. In some regions it can be, but this is not exactly what is happening in the algorithms. The second thing that And so while we were working on this problem, we came up with this intriguing question that we couldn't quite resolve. So let's say that you can run quantum phase estimation some limited number of times, but you can decide whether you will run it for many different configurations, or if you want to run it and for each configuration only a small number of times, or if you want to run it many, many times for small number of configurations. Which one will help your model learn? Either you can get very good information for a very small configuration, or you can explore the region, but you don't really have a good certainty at any point. In our case, we just fix the number of different configurations. We fix the number of samples we have in each one of them, but we couldn't really figure out whether you should focus on like this exploration of the region or more exploitation in very, very few places. So if you have some ideas about how to solve this, talk to me later. All right. So one other thing you could perhaps want to do with our generative model is to learn something about what is happening on the other side of an avoiding crossing or some phase transition. So we know that not all ground states are created equally, and preparing ground states of some Hamiltonians is much easier than for other Hamiltonians. So what one could do is that you gather decent amount of data on one side of the avoided crossing, and here we have so this is the ground state energy, this is the excited state energy. Here we have an exponentially small gap, or very, very small gap, and you would like to know how the ground states on the other side of the crossing look like. Can you do it? Can you somehow extrapolate from this data to what is happening on the other side? So yeah, this could be type of cheating, and if you spend some number of years working on ground state energy estimation, your inclination should be that this just shouldn't really be possible. So the way how you could intuitively think about it is that the model pretty much fits your existing data, and but if you have a phase transition, this is some type of a discontinuity. So you shouldn't be able to learn what is happening on the other side just by fitting your function in the smooth region. And yeah, and it turns out that that indeed is the right intuition, and we were able to prove this bound by mapping our problem into Grover Hamiltonian. So long time ago, I worked on adiabatic algorithms, and one of very few adiabatic algorithms where you can prove something about the performance is adiabatic algorithm for Grover search. So you can construct a Hamiltonian that initially starts with some simple Hamiltonian you will be projecting on the uniform superposition. And then when you evolve the Hamiltonian or the final Hamiltonian for S equals 1, then it will give you the ground state of it will be the projector on some unknown state. And if parameter S goes from 0 to 1. And we know that adiabatic algorithm for Grover search can solve the search problem in square root of n time, the same as standard Grover, but you cannot go any faster. We have a hard bound on Grover search. So we can use these results to show a lower bound for us for our sampling problem. And it turns out that you could, in principle, learn what this final state will be, or the states on the other side of the little gap will be. But to do that, you would need a very, very large number of samples before the gap. So this is the scaling with the minimum gap. And if the gap is exponentially small, then the number of samples you would need would be also exponentially small. So there is no free lunch really. This problem applies to quantum chemistry as well. And we were able to map one particle fermionic Hamiltonian on the Grover Hamiltonian. So what this tells us that we can really learn the molecular energy surface, but only by sampling from some easy region and then magically extrapolate to the more complex part of the Hamiltonian. Shouldn't really be surprising, but this is not really a magic bullet. So just to conclude, we came up with a generative quantum model. It consists of a quantum circuit and a neural network that we can use to model ground states of parametrized Hamiltonians. This is a quantum machine learning algorithm that learns from quantum states and then generates quantum states from some family. And even though it works in many cases, and it can help us and use in addition to existing algorithms, it won't really allow you to do anything impossible. And the impossible things would be solving ground states of Hamiltonians that would be otherwise QML hard, or extrapolating beyond what should be possible in physics. Thank you very much.
Any questions?
Yeah, so we will be needing preparing and inversely preparing the trial states, and we have a circuit to do that. Yeah. Sorry? No, so we are estimating the overlaps between our trial state that can be very good, but they can be very, not very good as well. So we are not using the amplitude estimation to train the model completely, only to compute the gradients. Yeah. Yeah, so yeah. Not really those ones. Yeah. Okay.
Any other questions?
You were saying a bit about the scaling of the gradients, and I guess increase the number of particles or states in the problem, and it would become like exponentially small.
Okay, so what happens is when you have like some, I think, are you talking about like the barren plateaus, the gradients? Yeah. So let's say you have some quantum model that will have some free parameters, all the gates where you don't know their assignments. If you have a model with deep enough circuits, and it doesn't have to be very deep for infidelity, then the gradients will be decaying as the number of qubits in the model.
Yeah, the question was, you said if you start from like Approximate or something, it's okay, but it's not going to be exponentially small overlap with the target state, but it will be exponentially small. And you expect like almost generically in many cases.
So yeah, okay. So once we go to really large system, if the hierarchy can break down.
Would there be some kind of other approach in like if you really want to scale this to like large end where you're not trying to do some gradient depending on a global quantity, just on local?
Yeah, so the question is, if you can really prepare the ground state, can you still prepare some state that will have a polynomial overlap with it in the regime of very, very large molecule? And there are some proposals for it, but it becomes more and more hand-wavy. So before Hartree-Fock, there are more complex solvable models, or approximation. You could use states from couples cluster, or other ansatz that chemists have, and they tend to work well for them. But in different regimes, you would probably use a different ansatz. People also talked about using adiabatic state preparation to prepare a state that should have some good overlap with the ground state, but that is just more speculative. So, but yeah, once the Hartree-Fock is just not really a good initial answer, it becomes more difficult. Yeah, Andrew?
Yeah, so I was thinking along kind of a similar line. So like, suppose, that we had some many-body system and I had a local Hamiltonian. I might be willing to consider accuracy in the ground state energy, where it's like basically energy density, energy per number of spins, for example.
Yeah.
And then want to get some nice approximations of that. And I would expect that in that case, you could do that with wave functions that were exponentially distant from the true Hamiltonian ground state.
Mm-hmm.
In fact, the spirit of about a couple of spins that that situation rise. So I suppose my question is, anyone like that seems like a very physically relevant problem. Are you interested either in an approximation to some finite region, or you're interested in energy per qubit instead of energy? I'm just wondering if people have thought about that in a similar kind of problem.
Do you think about the initial ansatz, or
so
as a problem?
About a situation where I only care about the answer to that sort of accuracy, and then in that case, essentially, things, this initial ansatz would have all the options we're talking about, but those ansatz are probably just much more accurate on that metric to begin with.
Yeah. Okay.
So the extra work the quantum computer has to do is also less, but I think it's still a place there.
Yeah. Yeah, no, like there is quite a lot of work in that space, so it's possible that people they think about it, but yeah, can't really give you a reference.